Okay, hello everyone. So my name is Zoltan Zvara, and I'm very happy that I can welcome you on my talk, which is going to be about data-aware Spark. Now I know that this title might be a little short here, but trust me that there is a lot of things going to be revealed here. So bear with me. But before we jump into it, let me do a quick introduction. Um, I have came from the Hungarian Academy of Sciences Institute for Computer Science and Control. And as a research institute, we do a lot of research and development for industry and partners as well. And the Ericsson flag at the front slide is something that proves this. So most recently, in the past few years, we had a lot of big data projects, including development and research on Spark as well as on Flink. But most recently, we started to work on a quality of service scheduler for Yarn, for example, and we also play around with a lot of other tools, NoSQL solutions and Kafka as well. As in terms of use cases, most recently, we have met with a lot of IoT and telecommunication use cases, and there basically the challenges were the data volume and the velocity. But here for this talk, the distribution will be the most interesting part. So let's just recap our agenda here. I'm going to outline you here our data skew story. I'm going to tell you how we have met data skew and how we try to tackle it in the first place. Now then, afterwards, I'm going to define some of the problems that we would like to solve here, and I'm going to describe our ultimate goal, which is going to be the data awareness, of course. Afterwards, I'm going to deep dive into our optimization engine, which is the dynamic repartitioning engine. I'm going to go through the architecture. I'm going to show you how all the different components work together to actually achieve this data awareness. Now I'm going to tell you a lot about how the repartitioning works, as well as along the way I'm going to show you a lot of micro and micro benchmarks as well. Afterwards, I'm going to show you how we manage to co-locate services in our huge Spark ecosystem and application cluster. Additionally, I'm going to touch some of the visualizations that we have developed for Spark and for other tools as well, and then I'm going to close my talk with the conclusions. So as for motivation, as I've told you before, we have developed a lot of applications, and these applications were basically aggregating IoT, social network, and telecommunication data. And we were very happy about these applications when we started to test them. Of course, we have run several simulations against toy data. And when we have deployed it against the real data set, we were very happy about that the application run very smoothly at the beginning. But after a while, surprisingly, we have discovered that it can become very slow or it might even crash. So of course we were thinking what went wrong. And for us it was of course data skew. So we have realized that we have some applications where the map sign combine from an operator perspective is really not an option for us. So we have groupBys and joins, of course. We have also realized that most of our data has this very nice power law distribution behind it. For example, Pareto or Zipfian. And afterwards, of course, if we look into Pareto, we can have a very nice phrase for it, like 80% of the traffic is generated by 20% of the communication towers. And we have realized that most of our data is really aligns very well to this 80-20 rule. So let's see what is the problem really at the Spark side. So even when you have a very even partitioning in some stage, when you use a naive hashing and you have some power law distribution or any other very skewed distribution, you are going to realize that you will not be able to hash the data uniformly. And the other problem is that some unknown partitions are going to contain a lot of records, and these partitions are really going to be unknown for you. Additionally, of course, this is going to introduce a lot of slow tasks. The other problem is that, of course, you don't know the distribution in advance. For most of our application, we realize that some offline simulation is just not going to work for us, some offline statistics. On the other hand, of course, when you are having a streaming use case, concept drifts are going to be very common. Of course, you can just fire up a Twitter analysis and you are going to be surprised how all the different tags are going to change by time. So based on this, we have collected a lot of features and goals that we would like to accomplish here, but in the meantime, we have realized that all these goals could be just collected into one ultimate goal. And this ultimate goal is for Spark to be a data-aware distributed data processing framework. Now, what do I mean by that? Of course, I'm going to break down all the features that we would like to have here. Now, as for feature one, we would like to have a generic NG-level load balancing and data skew mitigation engine. So why is it good for you? Because a lot of solutions have came out in the past few years trying to mitigate data skew, for example, at the SQL level, for example, putting a lot of statistics into the catalyst and so on. So the problem there is that you will not be able to adopt it to other APIs as well. And here we would like to have a very low-level, engine-level stuff that is going to work on any APIs built on top of it, so that you are going to have all these nice features for free for other APIs as well. Now, as for feature two, we wanted it to be completely online, so you don't have to mess with the statistics offline. This engine should accommodate to your system, to your data, to your application real time. So it is not going to require any offline statistics. And of course, you will not need to run offline simulations on the subset of your data. Now, as for features three, we would like to be distribution agnostic. And what do I mean by that? Of course, we have realized that most of our data is 80-20 rule, but not all of our data. And we wanted to have a generic solution so that we don't want to identify that, okay, this is a Zipfian distribution, but we want to solve and have a very nice load balancing in this regard. And we also want to avoid handling of special corner cases by that as well. As for feature four, we want to have a solution that you can use for batch and for streaming as well. And of course, the benefit of this is that you are going to have the same architecture, you are going to have the same logic, so that you can load balance, batch, and streaming jobs as well. And of course, you will be able to support unified workloads effectively. Now, as for feature five, we want to be system aware, and this is very exciting. The cool thing about this optimization engine is that it's completely pluggable. I'm going to show you here how we have plugged it into Spark, but it can be plugged into Hadoop MapReduce, of course, and we have also plugged it into Apache Flink as well, and it works flawlessly. So the thing here is that we want to realize how all the different systems trade off performance for different components here. And this optimization engine is going to receive a lot of feedbacks from the system. It is going to realize how much overhead would you have when you would need to reshuffle the state of yours real time. And as for our last feature here, I think most of you guys are on the same page with me if I say that Spark is really hard to configure for your cluster, for your application, and for your data as well. It takes a lot of hassle to actually do all of these things. So Spark is really not so out of the box. It is a very nice and interesting tool, but we want to be out of the box here, so the users really don't need to tweak anything. This optimization engine should be adaptive and should change configurations accordingly if it needs to. Of course, all we need to have is just switch on data awareness for Spark, and you are going to have everything for free. So as for the architecture, we have a master slave architecture, and what we are going to do is that whatever system you have, I'm going to talk about in the Spark case here, you are going to, for each task that you are going to deploy, you are going to approximate the local key distributions and statistics. Periodically, you are going to send all these back to the master, and afterwards, the master is going to collect and aggregate all these global K distributions and statistics. And then when the master sees fit, it is going to construct a new hash function. It is going to deploy it back to the slaves for further use. Now, from the driver perspective, we have something like the repartitioning tracker master. Now, it has been plugged into Spark, and it is part of the Spark environment, actually. And it is going to listen to job submissions and stage submissions as well. It is going to hold a variety of repartitioning strategies for jobs and for stages. And it is going to decide actually how to repartition the data and actually when to do this repartitioning. Additionally, as I said, with the system awareness, it is going to collect a lot of feedbacks from the system to actually learn how to adopt and how to refine all the hash functions. So from the executor's perspective, we have these tracker workers, which are part of the Spark environment, and it is going to store these so-called scanner strategies, which are actually received as part of some strategy from the repartitioning tracker master. Now, this tracker work is going to construct these scanners, and this is going to bind these scanners into the task metrics that you have for each task, where actually we collect all these data characteristics and statistics. And it is also going to define a very nice interface for these scanners to be able to actually send all these statistics back to the driver. Now that you can ask, okay, but how do we actually collect all these statistics? How do we actually approximate the key distributions here? So for that, we have developed a very nice strategy that is similar to counter-based sampling strategy. But we have fine-tuned it to actually be not sensitive to early or late concept drifts. Additionally, the sampling strategy should not put too much overhead to the system itself, of course, because it is going to run on the map side. We don't want to put too much overhead to the system itself. We don't not want to do less by trying to do more here. Additionally, it should be scalable, and for that we have utilized a very nice backup strategy that I'm going to outline you here. Of course, this sampling strategy can accommodate to batch and to streaming as well, but you're going to get the hang of it, how it actually works. So basically what we have is a bunch of counters for each keys. We're going to approximate the frequencies in these counters. Initially, we are going to have a sampling rate, which is going to represent the probability in which we are going to record any given key into this histogram. And when that happens, we are going to increase the corresponding keys counter with this sampling rate value. Now, after a while, of course, we are going to let this histogram to go a little bit. But as you may notice, we would like to handle data skew, load balance somehow, so that we are going to look for the bad guys for the really prominent keys, like when you're playing with Twitter data, like Madonna or Bieber or whatever. So if we see that we would like to add too much keys to this histogram, we are going to initiate our backoff mechanism, and we are going to reduce all the frequencies for all the keys, and also we're going to reduce the sampling rate with the same backoff factor as well. But then we're just going to slow down, but we are going to let this histogram to grow a little bit. So if we see that we would have too much keys, we are going to initiate a truncate mechanism. We are going to reduce all the frequencies and the sampling rate as well with the same backoff factor. Now, as for the complexity sensitive sampling, we have realized that the reduced runtime can highly correlate actually with the computational complexity of the value for a given key. So first, we wanted to calculate actually the complexity of the value. We tried to calculate the object size in the JVM. Now, it is very messy. It is very hard to do so. And actually, it is going to show very little correlation to the actual computational complexity which you have on the next stage. So our solution is basically that if you see that the user object is something like the waitable, so that it can compute its complexity, let's just use this complexity sensitive sampling, so that each time when we increase the counter for a specific value, we're also going to consider the value's complexity. Now, a few numbers about the scalable sampling. Of course, we have optimized it with micro benchmarks. We have realized the main factors are the aggressiveness of this. We change the aggressiveness adaptively. The initial sampling rate, your backup factor, and etc. based on your application, on your data, and on your use case, of course. And we also realize that the other main factor is actually the complexity of the current stage. So if the current stage that you are running this sampling on is very complex, you're not going to put too much overhead there. So actually, of course, it is going to somehow affect the runtime of the current stage, which is the mapper. And we have realized that if you let this mapper just to go forward till the end, it is going to add about 5 to 15% to the runtime. But when we are on a batch use case, we are going to switch it off after we have initiated the data awareness, when we have repartitioned everything. So we're just going to throw it out from the code path. So in practice, it is going to add way below 1% to the actual overhead. Now, of course, and as for streaming, what we do is something like we're not going to run it every time, but we are going to predict when we are going to see a skewed data or not. As for the decision of the repartitioning, so actually it is, of course, the goal of the duty of the repartition tracker master. This is going to initiate or use different decision strategies, like it is going to consider the number of histograms it needs. This is going to consider the distance from the uniform distribution. In addition, it is going to take a lot of preferences into consideration, like how to actually create this new hash function for this application. Now, for the construction of the new hash function, now that you can ask, but how do we actually construct the new hash function? Now, let's say that this is the global histogram that you would see on the driver. Now, based on the statistics that we have collected, and based on the number of records that we saw, you can define this so-called level, which is going to represent the number of records that you would have in each partition if you would be able to completely uniformly balance the data. So this is the level that we are going to look for here. So what we do is we are going to take some of the top prominent keys, and we are going to hash them into some of the first partitions. And if we see that some key would be very close to this level, we are going to hash this key exclusively into this partition so that we are not going to let any other keys to go there. And for the other keys, if we see that we have some space there, of course, we are going to initiate something like a probabilistic hashing here. We're going to hash a key there with the probability proportional to the remaining space to actually reach this level. And for the other keys, if we see that they are really close to some form of a uniform distribution, we are going to do a probabilistic hashing there as well. So a few numbers about the new hash function. Of course, it is going to be more complex than the hash code. We'll need to evaluate it for every record. But we have did a lot of micro benchmarks. And for example, for string, if you have more than 500 partitions, the key isolator partitioner is not going to perform that much bad in contrast to the hash partitioner. So, of course, because in practice, you're going to have a lot of other overheads on your system. This is going to add a negligible overhead under 1% to the actual runtime. Now, what do we do when we have the new hash function? We are going to reorganize the previously naively hashed data, or we are just going to buffer the data before we would hash it. Fortunately, it is usually going to happen in memory and usually going to add 1 to 8% overhead, usually the lower end to the complexity here. And for streaming, this is what we do for Bash, but for streaming in Spark, it is very easy to change the hash partition in the dstream graph. So so you are going to get this repartition mechanism in streaming for basically free, because of the very nice mini batch nature of Spark. So a little groupBy in Bash mode. Actually, when you run this in streaming, you are going to have the same stuff. We're going to do some groupBys on tags from listening stream. And what you're going to see for the naive case is that when you set the number of partitions to 17, the size of the biggest partition is going to be around 134 million records. Now, when you switch on dynamic repartitioning, we have only observed 3% map side overhead, so not that much, but with the same number of partitions, dynamic repartitioning, we're able to cut down the size of the biggest partition to around 83 million records, and this is the 38% reduction that you can have there. Now, of course, when you have the nice solution, you can increase or increase the partitioning of your job. You can over partition, but there you're going to have a bunch of over partitioning overhead and blind scheduling as well. So basically, you are not going to gain that much. As you see, naive solution is not going to get even close to dynamic repartitioning. Now, as for a batch join, let's just join tracks with tags on a similar data set. So of course, the track data set is going to be skewed because a lot of pop music is going to be very popular. So if you set the number of partitions to 33, you're going to realize that the naive solution were able to cut down the size of the biggest partition to a little more than 4 million. But if you switch on dynamic repartitioning, you were able to cut down the size to around 2 million. So this is the factor of 2 that you can get as a gain in terms of speed. But of course, you can easily realize a scenario, and this is a very average scenario. You can easily realize a scenario where you would have two or some of the top prominent keys accidentally hashed into the same partition. And of course, that case, that is not an average case, but if you are very unlucky, you can get a lot more, like up to 4 or 5% in runtime using dynamic repartitioning. Now, a few words about tracing in this regard. So, what is the goal of our tracing was? The goal is to actually capture and record the data points lifecycle throughout the whole execution, so that we can do some tweaks on our huge Spark ecosystem. So basically, we have rewritten the Spark core to actually handle some form of wrap data points. So instead of internally Spark just throwing around your type, each one of your record is actually wrapped. And the Spark core is going to apply functions on the payload where your data actually is. Now, when you extend this wrapped object, and we have extended it to be able to trace data points, each record is going to be a traceable object. And now, along the way, when we apply the function on the payload, we are also going to build and report some form of a trace. So we change this wrapper class, and then we're also going to have some form of a trace next to the payload. Of course, not all the records are going to be traced. It would mean too much overhead, but some portions of the records are really traced here. As for the implementation, it allowed us to have a very deep form of profiling, because we have a lot of Spark applications that interact with each other. And we report these traces to an external service, but these traces can be piggybacked next to the payload as well. And then afterwards, you can have a very nice graph extracted out of it, so that you can realize where your bottlenecks are, and actually how are these data points created, where these data points travel, so that you can improve the co-location of different services in your Spark ecosystem. Because we are not just throwing data around, but each data point might interact with an outside service, a lot of outside services. It can go into Kafka and another time into some Spark applications again. So let me add the last feature here to this data awareness, which is to actually provide data characteristics, all that we have gathered to be able to monitor and debug applications. We wanted to enable our users to actually sneak peek into the data flow. Additionally, we wanted to enable our users to be able to debug and to monitor applications more easily. Now, what we did in this regard is that we have made all the new metrics and statistics available through the Spark REST API, so that you can ask something like, okay, what happened in the last 3 seconds? And you're going to have a bunch of task events thrown at you. We also collect the block fetches, which occur during the shuffle phase. And this is how data characteristics look like when you query against it. And this is how local block fetch infos look like, for example. Now that you can ask, okay, but why do we do this actually? And the answer is to have a bunch of or a set of nice visualization tools which can show you actually a lot of features and bottlenecks of your applications. So let's see how the repartitioning looks like actually in the visualization. So let's say that you have some stage and you are using the naive hashing. What you are going to realize is on the reducer stage or side is that you're going to have a bunch of heavy keys that are going to create a lot of heavy partitions. And these are going to introduce slow tasks. And when you switch on dynamic repartitioning, you are going to realize that the optimization engine decided to hash some of the top prominent keys exclusively into one or few partitions, so that the heavy keys went exclusively into one partition, the heavy keys are alone, so that you were able to cut down the size of some of your biggest partitions. As for the conclusion, as you have realized or saw, our dynamic repartition can really handle data skew dynamically on the fly on any workload, and basically it can handle arbitrary distribution as well. As you saw, with a very little overhead, load balancing can be handled in a natural and in a general way. Tracing, of course, can help us to improve the co-location of related services, and visualizations can aid the developers to understand issues and bottlenecks of different workloads. And but I think the most important takeaway for you today is that making Spark data aware really pays off. Okay, thank you very much.
Any questions? Do you want the mic so everyone can hear you?
Thank you for the talk. It was really interesting. And I have a question about the repartition. When you were using the term repartition, you mean how you distribute the data when you do like a reduce kind of operation, is it?
Sorry, what kind of operations?
Like,
Yeah. Yes,
it's
correct.
repartitioning when you do the shuffle across the network and so on, right?
Yeah, basically at the very low level, when you're just looking into MapReduce. On the mapper side, of course, when you have completed your pipeline, you are going to just pick a hash function and you are going to hash this data into different buckets. So all we do is completely agnostic to APIs. What we do is we just change the hash partitioner to a custom partitioner. Each time that we see that your data will skew over time when you're using streaming, when you would have a concept JIPs, for example, if we see that you would have a very unbalanced partitions for the next stage, we are going to change the hash function on the previous stage.
Any other questions? We could probably take one more and then you guys could go get lunch.
So this all looks really nice. So how do we start using all of this? Is there a library already, a software package?
Yeah, so we plan to open source this library so that you can put it onto your favorite system. I hope that the Spark community will accept this as an addition to Spark. It would be really cool to create a PR against it. Of course, first we would need to create an issue for that. I think it would be nice to have an issue for it, of course, so that we can progress, so the community can help us tweaking this library, evolving it, and so on.